Good evening, everyone. Great to see so many of you here. So, as Chris said, today I'm going to talk about what's happening with analysis and design rules. So I'll start off with a brief review of the activities of FIB Commission 2, and then I'll look at some technical developments focusing on the critical shear crack theory, which is going to be incorporated into the 2023 revision to Eurocode 2. And I'll also look at some developments in Bond and how they might be incorporated into the Eurocode. So this slide shows the structure of FIB Commission 2 on analysis and design. And you'll see that there are a total of 10 task groups which cover all aspects of the design and analysis of concrete structures. And the membership of the task groups is made up of leading academics and industrialists. So I really would encourage you to get involved with one of these task groups. Personally, I've found it a very educational and fascinating experience, and great to get to know some of our European colleagues. In terms of outputs, the model codes are a key output from the FIB commissions. So these present new developments and also serve as a basis for future design codes. So Model Code 1990 heavily influenced the development of the current Eurocode, and Model Code 2010 is heavily influencing the current revision to the Eurocode. At the moment, the main work of the various commissions is Model Code 2020, which will provide a unified framework for both design and assessment. The other output of the commissions are FIB technical bulletins, and here I've just listed two upcoming bulletins from Commission 2. The first now published is on beam shear, and then the other is on Bond. So these are a collection of state-of-the-art papers, largely written by members of the task groups. I'm a member of task group 2.2, ultimate limit state models, and in particular I'm a member of working party 2.2.1, shear in beams, which is chaired by Ozzy Bayrak from Texas, and also working party 2.2.3, punching and shear in slabs, chaired by Aurelio Muttoni from EPFL in Switzerland. What I want to do now is just to briefly fill you in on some recent developments in shear and also how they will affect Eurocode 2 in its 2023 revision. So my involvement in this has been as a member of Task Group 4 of SC2WG1, which is or was responsible for revisions to Eurocode 2 relating to shear, torsion, and punching. And TG4 was shadowed by FIB Working Party 2.23, punching and shear in slabs, chaired by Aurelio Muttoni, who's also chair of the project team for the revision to the Eurocode. So quite a lot of overlap in membership between those two committees. And so the FIB Working Party had a significant input into the revisions which have been adopted into the draft Eurocode. So as you know, in Eurocode 2, the shear resistance provided by concrete in beams without shear reinforcement and also for punching shear is assumed to depend upon the flexural reinforcement ratio raised to the power of 1/3. In Model Code 2010, there the shear resistance provided by concrete is assumed to depend upon the strain in the flexural reinforcement. And in TG4, we recommended that the 2023 revision to Eurocode 2 should adopt the strain-based critical shear crack theory of Muttoni for shearing beams without shear reinforcement and also for punching shear. So a key feature of the critical shear crack theory is that the punching resistance of slabs is related to their rotation, which controls the width of the so-called critical shear crack. So this animation here just illustrates the key concepts of the critical shear crack, which is the bold crack shown there, and the width of that crack increases with increasing slab rotation, and as the width of the crack increases, the shear resistance provided by aggregate interlock reduces. This slide here illustrates the basis of the method. So the blue line represents the shear resistance, which reduces with increasing slab rotation. The other lines represent the load rotation response, with lines corresponding to 0.5%, 1%, and 1.5% flexural reinforcement. And what we see is that the failure load is given by the intersection of the load rotation and resistance curves. So each of the blue blobs corresponds to a predicted failure load. And we see that the effect of increasing the flexural reinforcement ratio is to reduce the deformation or the rotation of the slab, which leads to a reduction in the critical shear crack width and hence an increase in shear resistance. This slide gives the equation given in Model Code 2010 for shear resistance provided by concrete. So the first term, the coefficient K psi, that term relates the shear resistance to the rotation of the slab. So this term here defines the rotation, also proportional to the square root of the concrete strength. And B0 is the basic control perimeter, which is positioned at half the effective depth from the column face. In Model Code 2010, there are 4 levels of approximation. So there's level of approximation 1, which is intended for initial design. Levels 2 and 3 are intended for design, whereas level 4 is intended for detailed structural assessment. So in levels 1 to 3, the code provides a formula for calculating the slab rotations, while with level 4, the deformation of the slab can be calculated using nonlinear finite element analysis. And we'll see in a minute the benefits that gives us. So for level of approximation 2, the code gives us this equation here for calculating the slab rotation. And we see that the rotation is proportional to the radius of the line of radial contraflexure. So this is influenced by the slenderness of the slab, which is not considered in the present code. And we also see that the resistance depends upon the ratio of the design moment within the support strip to the moment of resistance raised to the power of 3/2. This slide shows a plan view of the simple flat slab building, and it shows that the elastic radius of contraflexure is positioned at approximately 0.22 times the slab span from the column center line. So punching shear resistance is typically determined in laboratory tests of small-scale specimens intended to simulate the slab within the radius of elastic contraflexure. These tests are actually conservative because they don't account for the beneficial effect of the surrounding slab. And here there are two beneficial effects that increase punching resistance. So first of all, we have compressive membrane action. And this comes about because cracking of the slab in the hogging region around the column leads to lateral expansion, which is restrained by the surrounding slab. And this generates radial compressive stresses, which increase the punching resistance. And the other benefit comes from flexural continuity. And so here we have a redistribution of moment between the span and the support following cracking and yielding of reinforcement. And this leads to a reduction in the radius of contraflexure, which leads to a reduction in rotation and hence an increase in punching resistance. So in the next few slides, I'm just going to show the results of some nonlinear analysis using level of approximation 4, which demonstrates the enhancement in punching resistance due to the slab continuity. So in this slide, I'm showing a conventional punching shear specimen where this slab here is intended to simulate the slab within the elastic radius of contraflexure. So in this analysis here, first of all, going to use the critical shear crack theory to calculate the shear resistance of a conventional test specimen. In this diagram here, I'm simulating an internal bay of a flat slab, and I'm taking advantage of symmetry to model 1/4 of the slab. So after calculating the resistance of the equivalent test specimen, I'm going to look at the benefit that we obtain from continuity by modeling the full internal bay. And so first of all, I'm just going to assume that at mid-span we have rotational fixity, and then in the final analysis I'm going to assume we also have axial restraint. Okay, this slide shows the analysis of the idealized test specimen. So the gray line here shows the resistance calculated with model code 2010. The black line represents the load rotation response, and the failure load is given by the intersection of those two curves. In this slide here, I've added in the response of the continuous slab. So here we're simulating the internal bay with rotational fixity at mid-span. And the effect of modeling the complete bay is to give a stiffer response. And so we see that there's an increase in punching resistance due to the reduced slab rotation. And then in the final slide here, I'm showing the beneficial effect of the compressive membrane action, which has reduced the rotation even further. So you can take account of this benefit using model code 2010 level of approximation 4, but in the revised Eurocode, it gives a simplified formula which allows you to take account of this benefit. When it came to drafting the code, it was felt that it was too much of a step change to introduce curves for resistance and rotation. So through a lot of algebraic manipulation, Professor Muttoni and his team recast the critical shear crack theory, a contribution for the concrete, into this form here, which you'll see looks very similar to the current design equation. The difference being that we've got this term here, ddg over AP, which represents the slenderness of the slab. The term ddg takes account of the size of the aggregate, and it can normally be taken as 32 millimeters for aggregate greater than 16 millimeters, but with high strength concrete, it is reduced. I want to move on now and briefly talk about Bond. So this is the work of task group 2.5, and the key document here is FIB Bulletin 72, which gives the background to the lap and anchorage rules in Model Code 2010. So this bulletin is informing possible revisions to laps and anchorage in the Eurocode. This is still a subject of considerable debate and discussion, and the key area of concern is the choice of safety format, and this is something that Charles Goodchild and myself have been and are involved in. So this slide here shows a simple pull-out specimen, and the key point is that from axial equilibrium, we can calculate the average bond stress along the anchorage length of LB. In Bulletin 72, it gives this equation for calculating the stress in the reinforcement bar at anchorage or lap failure. So looking at this equation, we see that the strength of the lap depends upon the concrete strength. It's related to the bar diameter, and also it depends upon the lap length as a multiple of the bar diameter. The term in the square bracket accounts for the effective cover, bar spacing, and confinement provided by links and secondary reinforcement. So the equation for STM can be rearranged to give an expression for the average bond stress along the anchorage or lap length. I've also written at the bottom of the slide there the average bond stress corresponding to yielding of the reinforcement bar. So in this slide here, I've plotted the equations for the bond stress at failure for a 10 millimeter bar, that's shown with the blue line, and for a 25 millimeter diameter bar, shown with the red line. Also shown is the bond stress required for reinforcement yield. So looking at the chart, we see that the average bond strength reduces with increasing bar diameter and also increasing lap length. The lap length required for bar yielding is given by the intersection of the coloured lines with the black line, which represents yielding. So returning to the Eurocode, we start out with this equation 3.1 from Bulletin 72, and this can be rearranged to give the required mean lap length. So that equation has been rearranged and placed in the current revision to the Eurocode, sorry, the computer's getting a bit bananas. And this equation gives us the required anchorage length expressed in terms of the concrete strength, the bar diameter, and also the bar spacing and cover. So the key decision to be made in this equation is the choice of the coefficient shown in red at the beginning of the equation. And so currently that's taken as 50, but suggested values range between 45 and 65, with the value of 65 determined from a reliability analysis. And as you might imagine, this has given rise to a lot of a debate between more pragmatic and more theoretically minded engineers, because it has a big effect on the economy of reinforced concrete construction. So to summarize, the work of FIB Commission 2 is very influential in the development of new design rules. We saw that the current Eurocode was greatly influenced by Model Code 1990, and the current revision is being influenced by Model Code 2010. And finally, the future work of Commission 2 is largely focused on the development of Model Code 2020, which will provide a unified framework for design and assessment. So that's just a brief run through the work of Commission 2, and I hope I've shown to you the value of being on one of these task groups. You know, it gives you a chance to really find out what's going on, and more importantly, to influence it as well. Thank you.